Good morning to all of you. Welcome to this NPTEL's lecture series on Introduction to Smart Grid. In this lecture, today we will discuss on smart grid protection. Along with that, we will also discuss 1-2 different protection schemes which are dedicated for protection of the smart grid system. Now, if you see nowadays we have like different disturbances. If you could remember, in 2012 July, in India we have very large blackout, and due to that blackout where the India faced a lot of problem, and as far as the money is concerned and the economy is concerned. So, and that particular disturbance was due to the protection failure. And if you could see that here another issue is coming here, the key renewable sources in India, basically the wind and solar. If you could see, the wind is 54% and the solar is around 26% of the total renewable generation. And again, the India is targeting to install 100 gigawatt of solar and 60 gigawatt of wind by 2022. Coming to this aspect of this particular today's lecture, I will just discuss about the different protection schemes, and mostly I will discuss the adaptive protection schemes for the microgrid system. And before that, I will just want to define what is this adaptive protection scheme. The adaptive protection scheme is that particular protection scheme where the protection scheme will operate with the change in system condition. It will just adapt, it will change the protection philosophy or this relaying algorithms or settings of the relay according to the system change, according to the change in behavior of the system. And this is, if you could see here, this microgrid system, here we have this grid, the main grid, and here is our IBDR, that is the inverter based distributed energy resource, and here it is SBDR, that is synchronous based distributed energy resource, and here is the microgrid control center. This microgrid control center will receive the information from all the switches, like S1 is the switch or the circuit breaker which is connecting the grid and the rest of the microgrid network. And here this basically this R1 and R2, next we have R3, we have R4, R5 and R6. And here also we have this S2 and S3. All together, all the relays and circuit breaker information can be sent to the main microgrid control center. So, where we will take the final decision, or that particular decision is going to be more accurate and renewable. I mean, it should be very reliable for operation of the microgrid protection. Now, I just want to remind you, in the previous lecture we discussed what are the different protection issues if the renewable sources are going to be integrated to the microgrid system. And that is why we are talking about, like, we have to improve the existing protection scheme, otherwise there will be a failure of the relays and there will be basically uninterrupted, supply to the, we cannot maintain the uninterrupted supply to the customers. If we are going to have without any fault, the system is going to be like tripped, a line is going to be out of service. So, obviously we will not be in a position to supply power to the loads, right. So, that is the main aim. And major issues just I want to revise here. The first point is dynamics in the label of fault, and the second one is fault stripping and this blinding of protection. If you could talk about this dynamics, means if let us say we have different types of renewable sources like inverter based DGs, like solar based, and also we have small hydropower plants where we use the synchronous based systems or machines. In that case particular, if the fault will be incepted, depending on the types of renewable sources, the fault current label will differ, it will just change. Let us say for the inverter based DG, the fault current label will be clamped to per unit of the rated current, and in case of synchronous based DERs system, the fault current is going to be clamped to 5 to like maybe 7 per unit of the rated current. It is basically more in comparison to the inverter based DGs or renewable sources. So, keeping in that mind, if the fault current label changes depending on the type of renewable sources, so in that case we have to be careful and we have to take care as far as the relay algorithms are concerned. And coming to this fault stripping, earlier the system was radial in nature, the power was flowing from upstream to downstream, like from the substation to the load centers, and but due to the penetration of renewable sources, now the network is going to be, will face bidirectional power flow. Bidirectional power flow means the fault direction will change and the magnitude will be changed and phase angle also going to be changed. So, in that case we have to also take care as far as the relay algorithms are concerned, relay the logic which are embedded inside the digital relays, those logics should be taken care. Similarly, the blinding protection means the relay is not able to, there is a fault, but the relay is not able to detect as this is a fault due to the decrease in the fault current level. Let me clear here that mostly in distribution level we prefer the overcurrent relaying principle, and this blinding protection is basically the issues with the overcurrent relays. And due to this blinding protection issue, the overcurrent relay will see less amount of current, fault current, which may be below the setting value, the I set. So, in that case the relay will not be able to detect the fault. So, these are the different issues, and keeping in this mind, these issues we have developed to adaptive protection schemes. In the subsequent classes I just want to discuss about it. Mostly I will discuss about the directional overcurrent relaying principles, because the distribution network generally we use the overcurrent relaying principle, and after that the directional relaying should be added, embedded along with this overcurrent unit, because I will tell you in the subsequent slides that the directional relay adds the selectivity property to the overcurrent relaying principle, because in this integration of renewable sources the network will see bidirectional power flow, bidirectional current flow. So, that is why if we will use the directional element along with the overcurrent element, and it will help us definitely to select the proper line, the proper faulty section instead of the healthy section. Now, we come to this particular adaptive protection scheme what we have proposed, like here if you see that the earlier case, but here the main concern is that we have to know the mode of operation of the microgrid system, because this mode of operation means whether this microgrid is islanded from the main grid or it is connected with the microgrid system in the grid system. This microgrid which I have just highlighted, whether this particular system is connected to the grid through this switch S1 or it is disconnected from the grid, that is what the islanded operation of the microgrid system. Those mode of operations basically decide the flow of the current label, direction of the fault current. So, that is why we are interested whether this mode of operation is grid connected or it is in islanded mode of operation, right. So, these are the concern for, basically this mode of operation should be, this information should be present at the microgrid control center along with the relay information, along with the circuit breaker status information, and those are the concern. And to come to this point, as I discussed, that we have different types of mode of operation like grid connected mode, this is the islanded mode of operation, and sometimes transition to island and reconnection modes. After islanding this microgrid, we have to also reconnect to the main grid, that is what the transition, that is transition to island and reconnection modes. If you will see that islanded, already we have discussed in one of our 1-2 lectures that if this particular switch is disconnected from the grid, then this particular microgrid system is islanded, and if disconnected, that is the grid connected mode. Now, as I discussed that in this lecture I will focus the different schemes, basically that is the overcurrent relaying principle and also the directional relaying principle. Coming to this overcurrent relaying principle, the principle of operation of this overcurrent relay is, if this is IP is my set value I set, and this IF is the fault current which is basically measured by the overcurrent relay, then if this IF is greater than IP, so the relay has to take decision. And of course, different types of overcurrent relaying principles, but in general we use IDMT, this IDMT best overcurrent relay. This IDMT stands for inverse definite minimum time overcurrent relaying principle. The characteristic is like this IDMT characteristic along this x axis and y axis, this is y axis. So, this through y axis we generally take the time of operation of the relay, and along this x axis we took this current, fault current, or sometimes also we took this PSM. This PSM is nothing clock setting multiplier, that is the relay current I relay fault current divided by the I set. This ratio, this clock setting multiplier is nothing, it is ratio of the fault current which is seen by this relay to the I set, or that I set is nothing, we call it clock setting. This PS stands for clock setting and this PSM stands for clock setting multiplier. Now, this characteristics, as I said, this is IDMT characteristics, inverse definite minimum time characteristic. If my current fault current magnitude increases, the time of operation, this time of operation second, the decreases. That is why this is known as inverse. And why it is definite minimum time? Because this particular characteristics will not touch the 0 axis, x axis, it will maintain certain time. So, that is why this particular time which is maintained above it only the relay is going to operate. So, that minimum time is maintained. So, that is why this name is inverse definite minimum time type of overcurrent relay. Also we have different like very inverse characteristics based overcurrent relaying principle, or only this extremely inverse type of overcurrent relaying principles, but in general in industry we prefer this IDMT type of overcurrent relaying principle. And after that by this time of operation is calculated and we maintain this TMS, that is a time multiplier setting, which is the time of operation of the relay with respect to the time dial setting. What time we are maintaining? As if like this PSM, we also maintain the TMS, that is a time multiplier setting of the relay. Now, the very simple that this overcurrent relay operates if the calculated fault current is greater than my setting current, then the relay is going to react. But the point here is, as I said from the beginning, that if we have a microgrid system where this bidirectional fault current is going to be seen by the overcurrent relay. So, it may happen that some overcurrent relays like which are, so let us say this is a fault where basically if that particular fault is present here, this fault is here. If this fault, due to this fault, this particular relay R5 will see some amount of current which is going to be contributed by this particular IBDR, or also this grid is also going to contribute some current. And in that case we have to take care like what are the current directions and what is the magnitude of the fault current. Like say, let us say here is one fault, let us say this is F1, and this particular synchronous base DG will supply some fault current to this fault point. Now, this relay R5 will see some fault current as well as this R3 will also see the same amount of current, same amount of fault current. So, what will happen? This R3 will trip unnecessarily due to this fault F1, which is not desirable. And so, these are the different issues, and we have to basically solve using different principles, but here we have proposed that the directional element may be added along with the overcurrent relaying principle. So, that this directional relay will say that what is the direction of the fault, and the name suggests that the direction of the fault will be decided very clearly, so that we should not disconnect any healthy sections of the microgrid environment. We have to only disconnect the faulty sections. And that is why this directional relay is preferable in case of distribution network where the renewables are basically penetrated along with the overcurrent relaying principles. And we have to use together, like overcurrent relay and directional relay will be like an operation of AND. If the both the decisions, this is an AND circuit basically, and this AND circuit inputs to this particular AND circuit will be from the overcurrent relay, and also the input to this the AND circuit will be from the directional relay. So, if these two inputs like 1 1, then the final trip signal will be 1. If any one of the relay, basically the output of the any one of the relay is 0, then the output is going to be 0. That is the AND operation, and to make it more reliable, more accurate, the final decision, so we can add together. The decision of the two relays can be added together. Coming to this directional relay principle, how this particular relay operates, we generally take this voltage, the pre-fault voltage. This is basically the nominal voltage at the different buses like DG buses or the grid terminals or the load terminal, wherever we kept the relays. So, this Vp is the polarizing voltage, and why this we prefer this voltage as a polarizing quantity? Because during the fault situation, the voltage magnitude may increase or decreasing depending of the situation of the network, but the phase angle does not change much. It may change maybe 1 degree, 0.5 degrees, but however, at the same time during the fault current magnitude as well as the phase angle changes. So, that is why it is more preferable to take voltage as the polarizing quantity and this current as the operating quantity. For the directional relay, anyway we need two quantities, one is the polarizing quantity, other one is the actuating quantity or operating quantity. And how it operates? It will take the angle between the two quantities. This is my polarizing quantity PQ, and this currents like IF1, IF2, these two currents in front of the relay and behind the relay, these are the operating quantity OQ. This OQ stands for operating quantity and this PQ stands for the polarizing quantity. Now, if this angle between this current and the voltage is lying within 0 to 180 degree, if this angle phi basically lies between 0 to 180 degree, then this particular fault is going to be declared. It is basically behind this relay in this backward, this is backward direction of the relay. Let me draw one figure here so that the things will be more clear, that if you have a system like this, here one source and here one DG which is connected, this is my grid, and let us say we have a load point here, here some loads and here some loads, and this directional relay is located at this bus. This is bus A, this is bus B, and this is bus C. If this is my fault F1 and this is my fault F2, so due to this fault F1, the current which is contributed to this relay is IF1 here, and due to this fault F2, the current component which is seen by this relay is IF2. So, that is why the two fault components will lie in this direction, and if what will the angle between these two for fault F1, the angle between this Vp and IF1 for fault F1 position, and that will lie between 0 degree to 180 degree. If it is so, this relay will declare as if the fault is, this is my directional relay, and this directional relay will declare that fault is behind this relay, it is not in front of the relay. But if this phi is between 180 degree to 360 degree, then the fault is declared to be in the forward direction. Forward direction, that means it is in front of the relay, that is F2. So, this is a basic principle of operation of the directional relay. Nowadays, we have different techniques to declare whether the fault is in front of the relay or in the backward direction of the relay. Lot of techniques, many techniques are now available. But this is a very basic fundamental technique which is also still used in industry. And there are also demerits of this particular technique. If there will be voltage collapse, then it will be difficult to decide whether the fault is in front of the relay or behind the relay. Now, as I said that the different techniques are available for coordination approach. The coordination is nothing, let us say this is one source, a grid system, and here we have one bus and one load, here also one load, and here another feeder or line, here also we have some loads. Earlier the line structure was like radial in network. Let us say this particular line is protected by some relay R1. And this line is also protected by another relay R2. Now, for protecting this line 1, 2, 3, this line 1, 2, 3, this is line 2, 3, this is my line 2, 3. To protect this line, this R1 is called as primary relay. So, if any fault occurs here at this point, then this particular fault is going to be cleared first by this relay R1, and that is why this R1 is called as primary relay. If this fault is not cleared by this R1, then it is going to be cleared by this R2, and this R2 is known as backup relay. So, here I just want to mention R1 is the primary overcurrent relay, and this R2 is nothing, that is the backup overcurrent relay. Now, what is the point? What is this primary and backup? Again we will discuss. Now, this, as I said, if any fault is going to be incepted in line 2, 3, this relay R1 should react as quick as possible, and the time of operation may be within 0.2, 0.1 depending on its TMS and clock settings, right, because as I said that every overcurrent relay has its clock setting multiplier corresponding to the fault current and also TMS. This PS and TMS are fixed. Now, depending on their clock setting and TMS, this relay will just find some fault current IF, and based on the calculation of the IDMT characteristic equation, it will calculate the time of operation which is required to trip for the relay. Now, if this particular relay R1 fails, then only this R2, which is the backup relay, will operate. And remember, this R1 operates first, then this R2 will operate in late within a time gap of 0.3 to 0.5 second. And this 0.3 to 0.5 second, basically this is a timing, it is not designed like that, it is a time of operation which is required for operation of the breaker which is present here for the line 2, 3. If this relay is failing, so it will take some time quickly before the relay R1, this R2 is not going to operate, or if R1 is failing, so very quickly it will not operate, it will wait for 0.3 to 0.5 second and then this R2 will react. That is the operational time for the backup relay, and that is why this time of operation T R2 is equal to T of R1, time of operation of relay R1, plus the circuit breaker time operation T circuit breaker, how much time is taken by this circuit breaker, plus if it is treated as X, some tolerance overshoot time. If I designs particular relay for particular time of operation, it may not operate due to different transient, different issues. So, there is some overshoot time of operation, and that time of operation may be sometimes 20% of time of operation this 2, that is the time of operation of the relay R1 and the time of operation of the circuit breaker, that is 20% of X. I just wrote this 2 as X, and that will be my backup relay time of operation. This is the time of operation between this primary and the backup. This particular methodology, this particular way of operation is known as coordination between the primary relay and the backup relay. So, this coordination is very important while we are discussing protection of the distribution network using the overcurrent relaying principle. And as I said that if this is a simple radial network, but if we are going to penetrate some renewable sources, like let us say at bus 3 we have added some renewable source DERs. So, what will happen? In that case, this relay R1 will not see if any fault will occur here. In that case, this relay R1 will see some different current. That means the setting of the relay is basically going to be changed, maybe for R1 and R2. So, today this much, we will discuss in the next class. Thank you so much.